I
Sorry, yeah.
just from the discussion we just started out with just about 10 minutes ago, I got a little bit of a sense of what you are working on, and I'm
Mm.
just a little bit jealous about all the stuff that you are doing.
Oh.
Uh, I wish I had mathematicians and the expertise that you will bring in my own lab. That would be super helpful.
Mm-hmm.
Um, so my lab is mostly doing experimental work. We do sleep deprivation studies in the lab, and you see pictures on the screen. I think you can see that, right?
Mm-hmm.
Uh, we see we do sleep deprivation studies in the lab, also in the field, and we learn a lot about how sleep and wakefulness and alertness and performance change over time in these experiments. And the observations that we collect in the lab, we try to then figure out from those observations how the biology that underlies it actually works, right? So we do a little bit of biomedical and omics related work as well, so biomolecular work, but we really use the data we see for behavior, for sleep wake patterns, and for performance to try to extract based on the dynamics that we see and also based on individual differences, which I won't be talking about today much, but is an important part of the story, and try to figure out how does the brain work? How does the body how the body and the brain control sleep and wake? What happens to performance? And how can we predict it
Mm-hmm.
when people are on a certain work schedule? They will become fatigued and will become impaired. So we can see that coming, and we can help them so that they will not be in jeopardy because of performance impairment. So we can keep them safe, so we can keep them working well and optimally.
Mm-hmm.
And when they're not, we can come up with solutions for them. So that's sort of the big picture of
Mm.
what we do. And what I've learned is that if you have data from experiments that are very informative about the temporal dynamics that you're studying, you have one part of the story, but it doesn't really come to fruition. You don't really understand what's going on until you start using mathematics to
Mm-hmm.
try to describe it, and then you get new insights. And today's story is a little bit about is one small part of a journey into getting new insights from using mathematics to understand the system,
Okay.
and particularly the sleep-wake system. So I am pretty certain that most of you have heard this part of the story before, but I'm going to walk through it just so that we have a shared basis of knowledge to start out with. And that has to do with the two process model, which is a very influential model in sleep science that describes, in principle, describes the timing and duration of sleep as it would naturally occur when people are not constrained by work schedules.
Mm.
So it tells us under a given circumstance, when will people sleep? How long will they sleep? When will they wake up? And when will they become sleepy again? And so um, that model comes from the early 80s, so it's more than 40 years old now. But about uh, 35 or so years ago, it was recognized that you could not only use that model for predicting sleep, but also for understanding sleepiness when you're awake. And the principle of how that works is actually very simple. So what you see in the graph on the left here is what we call the homeostatic process, as it plays out over a period of 56 hours of wakefulness.
Mm-hmm.
And it basically builds up in a saturating exponential fashion a pressure for sleep with every hour that you are awake. So the longer you're awake, the more pressure for sleep you will build up. And we don't really know exactly how that pressure builds up from a molecular perspective, but we know that the molecule adenosine is involved in some fashion. We know that for sure. And so there's something that goes on that builds up over time awake, and in this exponential, saturating exponential fashion, the longer you are awake, the more pressure for sleep you will have, right? But at the same time, humans are a diurnal species, and we should be awake during the day, and we should be sleeping at night. And our biological clock, therefore, maintains a circadian rhythm, as I'm sure you all know. And that circadian rhythm is trying to make it so that we try to sleep during the night and we try to be awake during the day, because that will be better for our survival in general, right? And so the biological clock then produces a pressure for wakefulness during the day to keep us awake, and a pressure for sleep at night to help us sleep. And that pressure for sleep from the circadian process interacts with that homeostatic process that also produces a pressure for sleep, and tries to make sure that we have enough sleep when we've been awake for a long time. Now, so the graph on the left shows you both these processes, the homeostatic process building up during a period of 56 hours of continuous wakefulness. And the red curve shows the up and down, the waxing and waning, or the rising and falling of that circadian pressure for sleep, which is greatest during the night and early morning hours, whereas the pressure for wakefulness, the counterpart of that, is actually greatest during the late afternoon. And these two processes together, in what, as far as we know, all approximately linear fashion, determine your overall pressure for sleep. And when we just add these curves up, we get the green curve in the graph on the right, right? It's a simple addition of these two graphs, of these two curves. And if we now measure performance in the lab on a reaction time task, which we call the psychomotor vigilance test, which is just really a very sensitive measure of performance impairment in the brain, and we do that across these 56 hours of continuous wakefulness, this is the kind of data we get. And of course, you see that it's an almost perfect match between what the model predicts and what we actually find. Now, I should point out that this is group average data. When you look at individuals, the pattern is always there, but some people are more vulnerable to sleep loss. Other people are more resilient. And so the curve is higher or lower for some people than it is shown here, but the pattern is always the same, pretty much. So in the early 90s, so about 30 years ago, it was actually generally believed that with the two-process model, we had pretty much figured out how theoretically sleep-wake regulation works and how performance impairment works when you're being sleep deprived, or when you put your sleep at a different time and you're staying awake at night. And for a long time, it was believed that that was the end of the story. But then in 2003, and when I was at the University of Pennsylvania, we published this paper, and that showed that that's only the beginning of a much more complex story.
I see.
So what you're seeing here is the daytime averages of people that were being kept in the lab for 14 days, and they were either scheduled to or either assigned to a schedule with 8 hours time for sleep every night. So that would be a normal, well-rested schedule, if you will. Or they were allowed to sleep only 6 hours per night for 14 days straight. So they were sleep restricted every day. Or they were restricted to even more, to only just 4 hours of sleep per night for 14 days. And that's the curve in red. The 6 hours is in yellow, and the 8-hour control group is in green. And what we observed is that if you're given 8 hours time in bed per day, you can get in approximately a little bit more than 7 hours of actual sleep in that time, of really good sleep. And we now know that that's not exactly enough to really maintain high performance every day. So we see a slight buildup of impairment in that green curve on the left. That is 8 hours time in bed is not just quite enough to actually maintain a stable level of performance, but it's almost enough, right? And it's not statistically significant buildup. But if you only get 6 hours of time in bed per day for 14 days straight, you see this gradual buildup of impairment. With every day you're in the schedule, your performance impairment becomes a little bit greater, your performance becomes a little bit less good. And so you start to build up this impairment in a not quite linear fashion. It levels out a little bit, it curves out a little bit. And in the 4-hour group, we see an even greater buildup of impairment, especially in those latter days. We see the performance impairment getting even worse. And that curve is almost entirely linear. And it just gets worse and worse and worse with every day. And so we see a dose response curve in two ways. We see a dose response that with every day you're in a schedule, things are getting worse. And also, the less sleep you get, the worse it gets, right? Now, to know how bad this actually gets, we also have this total sleep deprivation condition, which is the black curve that goes straight up in the left-hand graph. And you see the three little boxes, open boxes in that curve are 1 night with no sleep, 2 nights with no sleep, 3 nights with no sleep.
Okay.
And after 3 nights with no sleep, you can imagine that that's very difficult. That's very, very difficult to do. And you're very, very impaired, right? But after 14 days at 4 hours time in bed per day, you reach approximately the exact same level of impairment as that you can have reached after 2 or 3 days with no sleep whatsoever. So that's very significant impairment after 14 days with 4 hours time in bed. Very, very difficult to maintain that wakefulness for that long. And very, very much impaired to a point where if you weren't in the lab, it would be very dangerous.
Yes.
Now, in the graph on the right, we see subjective ratings on the Karolinska Sleepiness Scale. And the Karolinska Sleepiness Scale is a 9-point scale. People typically at baseline score themselves a 3 or a 4 on that scale. And as you sleep deprive them, they score higher numbers. They would score a 5 or a 6, maybe a 7. And what we see on that scale is a similar pattern, but not quite the same. So the 8-hour group basically says that 8 hours time in bed for subjectively speaking sleepiness, for how they feel, is just fine. They're right flat, right? It's flat.
Expected, yeah.
The 6-hour curve is not flat. It basically, after 1 day on 6 hours, people say, oh, that's not enough. I feel sleepy now. But then it levels out really quickly. And it never really builds up much further, right? It levels out after about 2 or 3 days. It sort of becomes nearly steady state, and it levels out. And then after 14 days, you're barely more sleepy than you were after just 3 days. It doesn't make much of a difference.
I see.
And with the 4-hour group, we see a similar pattern. It builds up a little bit higher, but then it also levels out. And the difference between 4 hours and 6 hours is not all that great. It's much, much smaller than the difference between 6 hours and 8 hours. So what that tells us is that in the subjective sleepiness, so what people actually experience, is they don't see that they're getting worse and worse on performance on the reaction time task. They're just thinking that they're kind of adapting a little bit. They also don't recognize that 4 hours is much, much worse than 6 hours. They don't really tell the difference as much.
I see.
And if you now look at what total sleep deprivation does, so that's the straight up curve in black. Again, the little boxes are 1, 2, and 3 days with no sleep whatsoever.
I see.
The Karolinska Sleepiness Scale is very skewed towards the top. And so you see that 2 and 3 days are very close to each other, but that's the extreme levels of sleepiness on that scale. It starts to skew and you get a ceiling effect. But you see that total sleep deprivation condition otherwise doesn't have that leveling off. It just goes straight up. Just gets from bad to worse to much worse, right? And so when you're acutely sleep deprived, as we had seen with the 2-process model, in subjective sleepiness, you can track that real well. You feel that, you notice that, and you report it. But with the chronic sleep restriction, the sustained sleep restriction that we see in the 6-hour and the 4-hour condition, instead you level out and you have this subjective experience that you are adapting, even though on the objective performance task, you are not adapting at all, and it gets worse and worse and worse.
I see.
So,
wow.
So our challenge was trying to figure out what's going on here in these temporal dynamics and how this relates to the 2-process model.
Okay.
Now, before I tell you the answer to that, I want to take a quick look at the actual sleep of these people in the nights when they were being sleep restricted. Let me make sure I can switch.
Oh, yeah.
Okay. Yeah. So, so here you see, first of all, on the right-hand side, on the bottom, you see total sleep time. And as I mentioned, if you get 8 hours time in bed, that's in the green curve, you don't really get 8 hours of sleep. You takes a while to fall asleep. You get a wakefulness a little bit in the middle. You might wake up a little bit early. So you get about, or on average, about a little bit, maybe around 7 hours or so of actual physiological sleep.
Okay.
At 6 hours, you get 5.5 hours of physiological sleep. And so you see that if you start restricting the sleep, your sleep efficiency, how well you can make use of the time that you have, becomes better. And at 4 hours, you get almost all of the time you spend in bed. Nearly 4 hours is actually actual sleep. So now your sleep becomes very efficient. But you will also notice that there is no temporal dynamic here. It's just these curves are pretty much flat, right? So they're not responding to the increasing performance impairment that you build up over those 14 days. The measurements were taken on days 1, 2, 4, 5, 7, 8, 10, 11, and 13 and 14. And through this period, we do not see any dynamic. There's nothing happening. It's just the same old every day. We see the same thing in REM sleep, which is makes up about almost 2 hours of the night in when you have 8 hours time in bed. That gets reduced to about 1 hour a night when you have only 4 hours of sleep, and it's a beautiful dose response. But again, there isn't much of a dynamic here. It's all just flat. In stage 2 sleep, we see something similar. Stage 2 is about half of your sleep, so that's about 3.5 hours for the 8 hour condition. Drops to about 2 3/4 of an hour, and then drops to a little bit less than 2 hours in the 4 hour condition. But once again, there is no dynamic here. Nothing changes over time.
Right.
Stage 1 sleep, we don't have much of. Stage 1 sleep is the first thing to go. Once you take that out, once you have less than 8 hours, the stage 1 is almost all completely gone. But again, there isn't anything going on here. It stays exactly where it's at. Slow wave sleep is different. Slow wave sleep is roughly about 1 hour of your sleep in a normal 8 hour night, a little bit more, but it's just preserved. So if you get 6 hours of sleep or you get 4 hours of sleep, you will still get the exact same amount of slow wave sleep. We had known that for a while. It's one of the reasons why people believe that slow wave sleep or stage N3 sleep, as we nowadays might call it, is one of the more important stages of sleep because it is actually preserved. You don't lose it when you start restricting sleep. And we've long believed that is the most restorative part of sleep. That story gets a lot more complicated based on these data, but importantly, it's preserved. It doesn't change. It's the same between the conditions, and it doesn't change over time. And then here we have delta power in the EEG of non-REM sleep. So that's the stage 2 and 3 sleep, and that's the amount of energy that we see in the lowest frequencies of the sleep EEG of those sleep stages. And we have long known that that is a marker of how efficiently you can dissipate the pressure, homeostatic pressure for sleep while you are sleeping. And we see that if we are sleep deprived acutely for 3 nights, and then we give people an opportunity to recover sleep, even in the first 4 hours of that sleep, there is a massive increase in the slow wave energy, the slow wave activity or delta power of that sleep. It's much deeper sleep. It's much more intense. You get much bigger energy in your delta waves, in your low frequencies of your EEG, and it's much harder to wake up from. And it's also much more restorative. But in the sleep restriction conditions, we see pretty much baseline levels of slow wave energy or delta power across all days. It makes no difference which condition you're in, and there is no dynamic response.
I see.
To speak of, and this has been really puzzling.
So Hans, this first 4 hour that black dot, I'm curious, kind of from the 0 hour TIB, they cannot sleep at all, right?
No, this is the recovery night afterwards. So this is the first night they get to recovery. You're right. This is the 4th day, and now they're sleeping. Sorry.
I see. They sleep. Okay.
Yes. So now they're sleeping. So here's nothing because there isn't any sleep. But here we give them a chance to sleep. You're right. Sorry about that.
Okay, gotcha.
So this is the night they get to recover. And the recovery night was not always the same. So it's not, we can't collapse these data over the entire night. But the first 4 hours, everybody received.
Okay, gotcha.
And there's this massive intensity in that first 4 hours of recovery sleep.
Right.
And you're right. In these first 3 days, there isn't anything because you're not sleeping.
Okay, good. Makes sense. Yes.
Yeah, thank you for catching that. That's important.
No, thank you. Yeah.
So the puzzling thing that we have now discovered by looking at these data is that acute total sleep deprivation, you get beautiful dynamics we can explain with the 2-process model. both in sleep and also in waking performance. And we can explain what happens with the sleep after they get a chance to recover after that. But in the chronic sleep restriction or the sustained sleep restriction paradigms, the 14 days on either 8 or 6 or 4, we don't really see any dynamics. We see performance impairment getting worse and worse and worse. We see subjective sleepiness leveling out, but there's definitely a response there, but it's just not dynamic very much. And then the sleep is basically not dynamically responding at all, right? And that's very puzzling. And we've always been wondering when we first published these data, what was going on here? And this is where mathematics turns out to become very helpful. So just to illustrate the conundrum or the difficulty we're having here. So this is the graph you've already seen before.
Yes.
The other graph that I just added to it are the two process model predictions of what you would think performance would be on average during the day, according to this model, to the two process model.
Yes.
Of course, in the 8-hour time in bed condition, nothing happens because it's well rested and you're in stable state. In a 6-hour condition, it takes you exactly 2 days to find a new equilibrium according to that model. And you level out at a slightly higher level of impairment predictions as the model predicts. 4 hours makes it a little bit worse. It takes about 3 days to level out, but then you stabilize. And the model now, you've got an exponential buildup. You have an exponential dissipation during sleep. These two exponential curves start to find a new equilibrium. You find it very fast. And the two process model basically says, well, it gets a little bit worse, but then nothing happens. So this looks a little bit more than what we saw for subjective sleepiness, although it's not a perfect match, but it's a little bit closer to that. But it doesn't look anything like this, right? It doesn't look like anything like the performance.
Yes.
And the question now again is, what is going on here? What are we missing? Because clearly we are missing something. So I started a long time ago doing some work for NASA, and NASA was interested in the same question because if you're doing space flight, if you're an astronaut, you will sometimes be kept awake for a long period of time, but most of the time, the problem with astronauts is they just don't get enough sleep on a day-to-day basis. Astronauts get about between 5 and 6 hours of sleep a night. We don't really know exactly why, partly because it's a noisy environment, but there's no particular reason why they shouldn't sleep very well if they put earplugs in, but they do. So they're getting not enough sleep. And the question, of course, becomes, well, how will astronauts do when they're sleep restricted? Is it going to be a problem? And so NASA asked us to start looking at this and try to come up with a model for explaining this.
Yeah.
And it wasn't very simple. We started with the two process model, and we decided to go with an ordinary differential equation framework. And here is how you can write the performance predictions in a differential equation form. It's a very simple model. So this is the change in performance over time, the P dot. And it's really just minus 1 over your rise time constant for that exponential buildup times the performance. So this, of course, if you work this out, is an exponential saturating exponential curve, right? And then there's the circadian modulation that you have seen from so this is the blue curve, if you will, or this is the red curve. And so that will give you your performance impairment, just like we saw in the earlier graph. And so it's a very simple model, very simple to work with. There's a similar equation for sleep. That's going to turn out to be just a dissipation of exponential dissipation like that. Oops, sorry, didn't mean to do that. So it just goes like that, and so it's the mirror image of this equation, but basically the same thing. And that is also why the two process model levels out, stabilizes so very quickly. It's just two exponentials, one going up, one going down, finding a new equilibrium very quickly, right? These time constants are in the order of, for wakefulness, it's in the order of some 8 to 16 hours, depending on how you fit the model exactly. And in the sleep period, it's about a 4-hour time constant. And so these two balance out really well and find a new equilibrium over days. And so that's why the curves that I showed you in the previous graphs come out this flat. They just stabilize really quickly. So what's important to note about this equation is that it has no history. Once you are at a certain level of impairment, the impairment in the future that you're going to have is only dependent on the time of day through the circadian rhythm, and then your current level of impairment. there isn't any particular history in this model. It doesn't really matter how you got to a certain level of impairment. Once you are there, then the two-process model predicts how what your future looks like, solely based on your present state. It doesn't matter how you got there. And that's, at the end of the day, is the key of the problem. Because when we have these sustained sleep restriction profiles, we started to learn that it does matter how you got to a certain level. If you get there through total sleep deprivation, or you go there through chronic sleep restriction, like in a 4-hour condition, as you've seen, you don't get the same kind of profiles, right? So history matters, but this equation does not have any history in it.
All right. Okay.
And that, at the end of the day, is the key problem. And so that's why you get the steady state within about 2, maybe 3 days. And that's not what our cognitive performance data showed when we did these sleep restriction experiments. So we've now identified from a mathematical perspective that we're missing something. And we believe that adding this missing component was going to be key to solving this problem. And that's what we did. And so here you see the same equation again that we started with, and we can generalize this equation by adding a second dynamic variable.
Okay.
Which we called U for no particular reason. It was just a letter that we had handy. And this is going to be a slower process. U is going to be a slower process. And U is going to drive where the asymptote for this homeostatic process is. It's going to change where that asymptote is.
Okay.
And that gives us now the history in the model. So if you work this out, then U, this is the wake part of the equation. U is also an exponential curve, but a much slower time constant, a much slower rate of change. P is just what it was here, but it has now a new component, which is the interaction with U, and that is going to change where the asymptote is that it moves towards. And now, of course, if you have a different asymptote because of how you were sleep deprived in the past, now you carry your history with you. For somebody who's going to be acutely sleep deprived, this slower process will not have much opportunity to change because it's too slow. It never gets there. So acute sleep deprivation will not really change the state of U because there's not enough time to do that because it is a slow process. But sustained sleep restriction over multiple days will allow the process U to change little by little, shift your asymptote in the model, and now your history will change, and therefore your asymptote will change. And that means where the asymptote that you converge to with your saturating exponential in P will change. And now you can have this buildup of impairment over multiple days. Right? So that's how we started. When I first worked this out, I didn't actually work out very well, but then a colleague of mine, Peter Macaulay, looked at the model more closely and noticed that there's a sleep equation version of this as well, which is the same, but just has different parameters. And of course, it's the dissipation part of it, where both the fast process and the slow process dissipate. And I had forgotten to put this element on the diagonal in there.
Okay.
And so I could never actually really get the model to predict both chronic sleep restriction and total sleep deprivation very well at the same time. I could fit one and not the other, or the other way around, but I couldn't really get them to do both well at the same time. So he then pointed this out and put the additional parameter in, and then said, look, when I do this, when I expand the model so I have 6 parameters, rate parameters, 3 for wakefulness and 3 for sleep, then the model has a new dynamic that I didn't know about before. You see that here.
I see.
So now this model, these are all model predictions. The thin lines are the dynamics within days, but they're not really important here. But the dots, the larger dots, are basically the predictions of the impairment that we saw in the first graph previously, right? But those are the daytime averages. And we see that with 8 hours time in bed, this is actually assuming that you're sleeping 8 hours and not just 8 hours in bed, but you have a pretty much flat line. So nothing changes, just like we would expect. With 6 hours, you get a little bit worse. With 4 hours, you have an almost linear buildup.
I see.
But now with 2 hours, which we have some data of that I'm not going to show you, but we only have a couple of days worth of that, but you actually start to diverge. This is no longer a gradual buildup that levels out a little bit. This is actually divergence. And the total sleep deprivation is just like what we saw in the actual data, is almost linear upwards. It's so diverging so fast that it's almost linear again, right? And so there's a bifurcation in this model where 4 hours time in bed is just about the tilting point. If you have more than 4 hours, you're ultimately going to level out gradually. It will take a long time maybe, but you will level out. But if you have less than 4 hours, like 3 hours or 2 hours or 1 hour of sleep per night, you're not actually ever going to reach a steady state according to these predictions. You're actually going to get worse and worse and worse, faster, faster, faster. And we know from personal experience from our daily lives that getting 6 hours of time in bed per day is doable. It's not great, but it's doable. 4 hours time in bed is very difficult. If you don't have a weekend in between, that's very difficult to maintain. But virtually nobody ever tries to sleep only 2 hours a night for more than a couple of nights because it's almost impossible.
Okay.
Right? It gets so difficult. You can't do it. And total sleep deprivation for more than 3 days is just, you just can't keep people awake that long. So this is what we discovered. And the bifurcation is given by this equation for the parameters. Doesn't really matter what they are, but basically it relates the duration of the day to this constant, which is the amount of wakefulness you can have before you start to diverge. And that amount of wakefulness turns out to be almost exactly 20 hours. So you can lose about 4 hours of sleep per night and just sort of be leveling or almost linear. But if you lose more, if you have less than 4 hours time in bed per day, you're going to see this divergence.
Okay.
Now, the question, of course, is this actually what happens in the real world? And it turns out that is exactly what happens in the real world. So this is data from Walter Reed Army Institute of Research, which is an institution in Washington, D.C. that was doing an experiment not much different from what we were doing at the University of Pennsylvania at the time. They were studying people for only 7 days of sleep restriction. They had a control condition, which was 9 hours time in bed, which you can see gives you pretty much an exact flat line. This is just perfectly steady performance. There was a 7-hour condition, which is just not quite enough. And this is a significant buildup of impairment, not a lot, but some. Here's 5 hours time in bed. So that's a beautiful dose response. But then when you go to 3 hours time in bed, you see this condition breaks away. It's not a beautiful dose response anymore. This condition actually escalates, right? It's not leveling out. It's actually escalating. 4 hours would have been here if they had studied it, a perfectly straight line. And then 3 hours breaks away. So this matches the predictions of the model. The other thing that's interesting about this experiment is that they looked a little bit more closely than we did at the recovery period. So this is now when people got 8 hours time in bed to recover, which is not a whole lot of sleep, but should be enough to actually at least dissipate some of the pressure for sleep. And what they found was, even though with this 9-hour condition, the 8 hours time in bed kept them basically where they were here. But this condition, 77777 and then 888, it didn't actually come back. It didn't reduce to baseline. 5 hours didn't do that either. 3 hours did it a little bit, but never quite back to baseline.
I see.
And initially, we thought that this was just an artifact of being in the lab for a long time and maybe not being very happy and not doing a lot of effort on the performance test anymore. But upon further reflection from the people in this group, so Greg Belenke and his team, they decided maybe something's going on here. Maybe this is another reflection of the fact that you carry your history with you. And it's basically a reflection of the fact that your asymptotes have not completely come down yet because they have long time constants. And you're still carrying your previous buildup of these asymptotes with you. And therefore, your baseline is actually changed to something that's less optimal. So I just want to show you real quick that the model predictions from the model that we've constructed to just this point kind of have, they're not a perfect match, but they're a pretty good match of the actual data.
Mhm.
So here's what the data that you've seen previously. I averaged the data per day now, but this is the raw data, group averages, but the raw data by time point. And here's the predictions.
Okay.
And you see that the 6-hour condition is a little bit more impaired than we predicted, but that's because this condition had 2 individuals were exceptionally vulnerable to sleep loss, and they didn't average out. We now know from other data that the 6-hour condition is actually a little bit more like here. So these are just 2 outliers in the actual data that carry this further apart. But other than that, it's a pretty good match. And here's the other experiment you just saw with the 9, 7, 5, and 3. Here's the predictions, and here's the actual data. And the actual data are noisier than the predictions, of course. But the pattern is pretty much well predicted, just like it sort of showed up. And the model also predicts that it takes longer to get back to baseline. It actually over predicts the duration of that a little bit in this version. That's because there is another parameter missing that I might talk about a little bit later on. But it captures the general gist of the phenomenon, right? It just looks a little bit more than like what we actually found. And the 2-process model would have done miserably bad on this experiment. It would have never captured it well. So we're on the right track here. And this is the actual estimate, the statistical estimate of that wakefulness constant. So it's 22.2 hours. So it basically says if you have less than 3.8 hours time in bed per day, you're going to see this escalation of impairment. And if you have more than that, you're going to see this leveling out, like here and here. And if you're at 4, then you're almost exactly on that threshold. Then it's pretty much linear. So, and of course, then we have the total sleep deprivation condition, which is, again, it's noisier in the real world than it is in the model, but it actually predicts it pretty well. And so this was the first time we were able to predict both total sleep deprivation and sustained sleep restriction, and also the recovery pretty well at the same time.
Okay.
You might notice that the recovery of the 4-hour condition here is a little bit bigger than we are predicting here. And that is, again, because there's still 1 parameter missing in the model, but I might get to that later. But the basic dynamics are now here. So we can now start to think about this model as a conceptualization of how the brain handles chronic sleep loss, as well as total sleep deprivation all at the same time. And that there is this history process in the system that keeps track of something that happened in your past. That is not part of the 2-process model, but it is part of this new model. And we can apply that to make some predictions about certain work schedules, because it's ultimately what we would like to do. Is we like to use this model, among other things, to make predictions about what people will experience when they're sleep deprived in the real world. And so what we did is we looked at somebody who's on a schedule for 4 hours time in bed for 5 days. So it's a heavy work schedule. They have to work really hard. Might be somebody who's writing a grant proposal for funding or something like that, or trying to get a paper out the door. We sometimes do this, right? And then we gave them 10 hours for 1 night in this simulation. This is a simulation to recuperate, and then another work week would start. And what the model predicts is that you get this buildup of impairment from baseline all the way up to almost exactly linear.
Okay.
And then the 10 hours time in bed will give you some recuperation, but not all of it, because you have this history with you that has this asymptotes being increased. So you don't fully recuperate to here, but only to here. And then after you build this up, so after you've done this, you start to do the next week, you kind of go on the same trajectory as if you had left off here. This point here and this point here. You're still carrying that asymptote with you. And so your buildup is actually almost exactly as if this night really wasn't there. And after 3 nights, you really have no benefit of this 1 night anymore.
Okay.
And it basically suggests that, well, first of all, 1 night for recuperation is not going to be enough, because you don't have enough time to get your asymptotes back to normal. Secondly, you still have this potentiation, this sensitivity to sleep loss that you carry with you into your next work cycle. And that has implications for how you build work schedules. And there's one particular way you can start to think about this, is that as if you are converging to a different steady state that incorporates your history, ultimately levels out if you're not sleeping too little, if you're sleeping
I
more than
see.
4 hours. And if you do this day after day after day after day,
Huh?
if you were to get about 6.4 hours time in bed every day, you would see
Uh,
over time this buildup, which is sort of
uh,
like the 6 hour condition that we've seen.
uh,
It's basically the same. You can also do 5 days with only 5 hours time in bed, and
uh,
then 2 nights for your weekend,
uh,
recuperate, and then another work week, and then on 2 days for weekend, another work week, 2 days for weekend. And you see the same pattern emerging,
I
as
see.
in you're building up over time. You're still carrying this history, and over the long run, that history is not all that much different whether you sleep the same every night, or if you're doing the short-term dynamics of multiple days of insufficient sleep and then recuperation, and then again and again and again and again. It kind of comes to the same thing. And at the end of the day, your longer term dynamics are dominating your short term dynamics.
I see. So kind of 2 days, at least we need 2 days of recovery, I guess. The 1 day is not enough.
Yeah, but even the 2 days ultimately don't really help you if you're not getting enough sleep overall.
Mm,
You're leveling out, but you're
mm,
leveling out to about this level
mm.
instead of where you were before, which would have been here,
I see.
right? So if you slept 8 hours a night every night,
Yeah, if we reach to zero, yeah.
yeah, you would have been right there.
Uh,
So the weekend will help you, but it won't help you get back to normal unless you have um, uh, plenty of sleep,
mm,
not just in the weekend, but also during other days.
mm.
And I suspect that many of us are living somewhere at this level of impairment all the time, because this red schedule is very typical for something we do in real life, and so we're probably actually performing at a level that's a little bit elevated for what we are really capable of. And if we slept more, that would cost us more time and would be a costly intervention because you can't work while you're sleeping, but you would be working at a better level. You would be less impairment, and you would be more alert, and you would have a greater ability to maintain your performance. So another prediction from this same reasoning is if you can carry your asymptotes with you, and we've seen in a 9 hour condition from the previous experiment that things actually are really good if you sleep 9 hours a day. You could also ask yourself, what would happen if I slept 10 hours or 12 hours a day? Would I be able to reduce my asymptotes so much
Mm,
that I now actually carry my history in a way that's going to be helping me?
mm,
And that is an experiment that was done also at the Walter Reed Army of Institute of Research, where they had two groups of people that they were being subjected to 3 hours time in bed per day for 7 days, just like the one you've seen before,
mm,
and then some recovery days. But before these people came to the lab, they were either put on their habitual schedule, so what they normally did during their normal days while they were working or doing whatever, or they were being asked to sleep at least 10 hours a night
mm,
for the whole week before they came to the lab,
mm,
to really try to bring down those asymptotes, to really try to bring down, to extend their sleep and reduce that history that they were carrying with them, and see if that would make a difference. And it
mm.
absolutely makes a difference, because now the experiment is exactly the same from here. But if you were previously sleep extended, you start at a better point, your baseline's better, you stay better through this entire experiment, and you recover faster.
Mm.
So prior sleep extension will actually help you do better when you're subsequently sleep restricted, and it will allow you to recover better because the asymptotes that you carry with you, your history, is a better history, and you
Yes.
carry that with you.
Mm,
So they call that banking sleep. It's not a very efficient way to actually make things better, but if you can imagine if you needed to do something really important
mm,
in a work week that has not enough sleep,
mm.
and the week before that you can get all the sleep you want. This might be a very successful way of making you really good during the week when you need to be really good.
Okay.
So I'm not going to walk you through this, but the full model is more complicated than what I just talked about. It's here's the equations for P during wakefulness and sleep. There is these are the P dots, and here's the P, here's the U. There's a constant here that is necessary for predicting not just things that like the PVD, but also other variables. I'm not going to really talk about that, but if you have the Karolinska sleepiness scale, the lowest value on the Karolinska sleepiness scale is a 1 and not a 0. So to get baseline for KSS for that model, for that variable, we put a 1 here instead of a 0. Then here's process U, which you have seen previously is an exponential buildup during wakefulness, exponential drop during sleep. And this here's where that bifurcation comes in. You can express this equation in terms of that bifurcation.
I see.
Then we have here's a circadian model. In this particular version of the model, that's a static or a non-dynamic circadian oscillation. We have a version of this which is dynamic, but it doesn't really matter much for these kinds of experiments. And we have a dynamic amplitude on it, and that's necessary because we know that when people are well rested, the circadian clock doesn't really impact their performance as much as when they're sleep deprived. And so there is a sigmoidal curve here that makes the amplitude of circadian rhythmicity bigger when you're sleep deprived. And then here are just this dynamic model and this circadian pacemaker are just put into these non-homogeneities that enter this equation here. So it's a little bit more complex than what I've talked about, but it's the same model, the same principles basically. So here's the prediction for performance. You can predict performance on the PVT, but we can also, with this model, the same model, predict subjective sleepiness. It just comes out with steeper because the time constants are different. Right, but it actually follows the same dynamic in principle, and it also has a bifurcation. But that bifurcation is at about 22 hours. So from a subjective perspective, from how you feel, it feels that you're actually adapting a little bit if you get at least 2 hours of sleep, even though objectively that's not true. We know that that's more like 4 hours, right? So here's this slow process. We now call that an allostatic process because really what this allostatic process is doing is changing the set point of your homeostatic equation. And that is basically a biological adaptation to insufficient sleep. And that is what allostasis is all about. It's changing the biology to preserve homeostasis. So this is really an allostatic process. Here's that dynamic, that circadian pacemaker with a dynamic amplitude.
Recording it.
And then, do you need to start it again?
Okay. What? Oh no, it's under recorded. I don't know what happened. Yeah, it should work. Yeah, please. Yeah, go ahead. Yeah.
And then here we just put these in these non-homogeneities, and you can add other drivers in this equation. If you have something like stress that you know affects performance, or high workload, or anything else that you can add that this non-homogeneity into the model, and it will still work, and work the same way. Just for if you were curious whether this model and the way it's parameterized actually works, the parameter estimates are remarkably well conditioned. So the correlations between parameters are very low. There's a little bit of redundancy in this corner here, but even for even that's not really terrible. We can improve that a little bit, and that's where that additional parameter that I talked about comes in. If we add that additional parameter, this also resolves itself, and then we get a little bit better prediction about the recovery part of the model. But it's really not worth talking about today. What I really want to talk about is the other part of the story is how does any of this happen in the biology, right? Because as I mentioned, once you start doing the mathematics, you should be able to get some insight into what's going on inside the brain or inside the body that makes it this way. And what's important to note is that, so if here's our performance and here's that slow process, that the way the model is configured, you have this interaction where this slow process feeds into this fast process. The way it looks on paper is like it's the other way around, so it looks like it's this way. But I will show you what the biology, we actually think it's going this way. And I'll show you that why that is so later on. There is another model out there that has this version and not this version. That's done by Andrew Phillips in Australia, in Sydney, Monash.
Monash, yeah.
Yeah. He has he developed independently of us a version of the model that has this, but that version does not have a bifurcation. Bifurcation comes from this version. And we can add this one in and make our model a little bit better, but it doesn't do a whole lot. But without this, you don't have a bifurcation, so then you can't predict the slow, or sorry, the really highly restricted schedules. You can't predict those very well. So we think what this represents, first of all, we know for sure what this represents is a positive feedback loop. And a positive feedback loop is very exceptional in biology. Most receptor systems that we have are actually negative feedback loops. Like, for instance, if you were to use cocaine, which I don't recommend you should do, but if you do that, then you downregulate your receptors, and then you need more and more cocaine to get the same effect, right?
Yeah.
And that's how you get addiction.
Yes.
Well, first of all, nobody's ever gotten addicted to sleep deprivation. And secondly, the model dynamics tell us that this is a positive feedback loop and not a negative feedback loop. And so we're looking for biology that has a positive feedback loop. And there isn't that many systems you can look at that have this.
Yes.
Pretty much all the neurotransmitters don't have that. They're negative feedback loops.
Yes.
But the adenosinergic system has a positive feedback loop. And we already knew that the homeostatic process involves adenosine. So we were thinking we need to start looking at adenosine. And there's a beautiful review paper by Radhika Bashir from Harvard that lays out that this system where adenosine and the adenosine receptor are both dynamic systems, and they're in a positive feedback loop. And the more adenosine exposure you get, the more you will build up your adenosine receptors. And then, of course, the more adenosine receptors you have, the more adenosine you can bind. And that is a possible way you could have this buildup of sensitivity. And it could be that the asymptotes that are changing over time are actually really your adenosine receptor density. Now, that story is going to be much, much, much more complicated, but the temporal dynamics kind of work really well with this as a possible system. So we explored that a little bit more. And we first of all looked at all the literature. And we know for sure now that in humans as well as in animal models, adenosine builds up with sleep deprivation, both total sleep deprivation and sleep restriction. So the adenosine receptor, we already knew that adenosine itself changes dynamically with sleep loss. And so the literature is starting to tell us that where we might be on the right track. But that leaves the question of how is it then exactly that this adenosine receptor density upregulates when you sleep? And we think we know the answer to that question too. So here are these same systems again. And I'm going to map those onto now to this diagram. And this diagram comes from something completely different, which is an explanation of how we think that performance impairment in the brain actually works in the first place. What we think is happening there is one of the hallmarks, one of the characteristics of performance impairment when you're sleep deprived, is that you have an instability in your ability to perform. The reaction time task that I showed you earlier captures this instability. And what we see when you're performing that reaction time task is that you become less able to produce fast reaction times, not always, but sometimes. All of a sudden, you get what we call lapses of attention, and you're slow to respond when you're just a second ago, you were really fast. Now you're slow. And then you're fast again. And so this instability, we have known that for a long time, but we never quite understood where that came from. We now think we may actually know where that comes from. And it comes from the fact that if you're processing information in a neuronal assembly or neuronal group, a neuronal pathway, that you are doing this synaptic transmission to process information, right? That involves the neurotransmitters going into the extracellular space. But with those neurotransmitters, you also put ATP out, the energy source of the brain. And that ATP, before it gets recaptured, binds briefly to the purine type 2 receptor. The P2X7 is the most important one. That receptor takes ATP briefly. And when that happens, you get a cascade of sleep regulatory substances that are being secreted into the brain. Most of those are immune regulatory substances also, so that's TNF alpha, it's IL-1 beta, it's probably BDNF, there's a bunch of other things. At the end of this cascade, you get an upregulation of NF-kappa B, and that upregulates the adenosine receptor. So the adenosine receptor, or the purine type 1 receptors, but the adenosine receptor type 1 is a purine type 1 receptor, gets upregulated at the end of this cascade. In the meantime, this extracellular ATP gets reduced to regular adenosine because this phosphorite groups, they need to be stripped because that's where the energy resides, and the brain wants it back. It reduces the ATP to adenosine. That adenosine is now in this extracellular space, binds to this adenosine receptor, which has been upregulated. And when that happens, this neuronal group is put into a sleep-like state, which we call local sleep.
Mm-hmm.
And when local sleep occurs, you can no longer do synaptic transmission, not in a meaningful fashion, and the output of this neuronal group will stop temporarily or become nonsensical, actually. And so you're no longer processing information, and that produces the lapse of attention. That produces that instability in your performance. So the use of this neuronal assembly creates this cascade of events that start with the ATP into the extracellular space, that gets reduced to adenosine, binds to the adenosine receptor, stops this neuronal assembly from working, and then you get this temporarily blockage of information processing. But in the meantime, that ATP binds to this other receptor, that releases this cascades of sleep regulatory substances, and that leads to this upregulation of adenosine receptors. And so the more you do this, the more sensitive to sleep loss you become, because you're building up this adenosine receptor.
Okay.
And that, of course, is the asymptote in the model that you're changing over time. Gradually, slowly, but surely you build up that adenosine receptor density, and it makes you more sensitive to sleep loss.
Okay.
So here's another picture of the same phenomenon put in this context of the brain now. So this, of course, happens between neurons and it's very small scale. So this is like, if you look really carefully, you can see it here in this magnification glass, if you had a really strong microscope. So we see this exchange of information and these release of ATP that actually binds on these astrocytes here to this P2X7 receptor. And that leads to this cascade of sleep regulatory substances that get released into the brain, and ultimately lead up to, well, first of all, ultimately put the brain to sleep globally, because it binds, it signals to this ventrolateral preoptic nucleus here that the ascending arousal system needs to be shut off so you can actually go to sleep. But before it does any of that, this actually upregulates the adenosine receptors. So you see that here with this NF-kappa B being the last step to upregulate the adenosine receptor. And that creates additional sensitivity to adenosine and puts this neuronal assembly to sleep much faster than it previously did.
Okay.
That's what we think the underlying machinery really is all about. Now, it turns out, as you are probably all familiar, that if you are really deeply sleeping, you're very densely sleeping, you're very intense sleep, and I wake you up, it takes you a little while to get back to normal. You have this what we call sleep inertia phenomenon. Yes. You're disoriented, and it takes a while for that to dissipate. And a long time ago in the 90s, Bennington and Heller posited that sleep inertia phenomenon is also related to adenosine, and actually as a side effect of the restoration of energy in the brain while you're sleeping. But if that's the case, then this adenosinergic process, we must always also be able to capture in the same paradigm, because basically what we've said we are doing is we're modeling adenosine dynamics. So we did that, and we added a component to the model where there's now a new dynamic variable, which is a very, very fast time constant that captures this sleep inertia phenomenon. Even during sleep, it already builds up, and then during wakefulness, it dissipates. And so we can capture that with the exact same model. and we can make them predictions. And now we see that we can actually capture the dynamics from moment to moment within the day, where you see at the beginning of every day, we've got the sleep inertia phenomenon. And we capture that pretty well. It's just one data point a day, so the data is a little noisy here, but we capture that same phenomenon with the same framework. So that's the most recent edition. We haven't published that yet. It's the paper is 1 week away from completion. So we think we're on the right track there as well. So I have exceeded my time. I know that I've run out of time here. So these are the papers that we've published on this model so far, just for your reference. And I'd be happy to share these slides with you. We are working on 2 other things right now. So we know that the recovery, our ability to capture recovery sleep is almost right, but not perfectly right. We know which parameter we need to add, and we've completed a paper on that. That's going to go out later this month or next month for publication. So we've dealt with that. We also know that we haven't got a dynamic circadian pacemaker in here yet. We have developed one. We haven't put it in the model yet. And the reason we really like to do that is that this model is already in use in aviation. It's being used by FedEx in its cargo operations, flying, and it's being used by United Airlines to schedule their pilots for civilian flights, for commercial flights. And so, but they can only use it right now for domestic operations because we don't have a shifting circadian pacemaker yet. And so what we need to do is, well, we now insert the dynamic pacemaker we already have developed, put that in the model, and start using it to predict both the sleep schedules that pilots will have when they're flying to another time zone, and the performance impairment that follows. And what's very interesting about that is that we have dynamic circadian models, as I'm sure you know. Cronauer developed a really powerful. There are some others out there. But they predict the dynamics of the circadian pacemaker as a biological clock, as an endpoint. In our model, that's just one small piece of a larger set of equations. And it turns out that you don't need the full complexity of the Cronauer model to really capture what we need for performance at a level of accuracy that is sufficient. So we've built a somewhat simpler circadian pacemaker. It still is dynamic. It still has the dose response or phase response curves and all those beautiful things that those models have, but it doesn't have the same complexity, and it actually works better in the context of predicting performance. We're not really interested. We're not really interested in probably need to turn that off somehow.
I think someone, I just unmuted him. Okay.
We don't really need to predict like the melatonin secretion or anything like that. We don't really need to know what the circadian pacemaker is doing, but we need to know what the effect of the circadian pacemaker on performance is doing. And those turn out to be not the same thing. They're related, obviously, but they're not the same thing. So that's what we're working on. And when we've done that, we are probably going to take a little bit of a break and see if we can come up with any new ideas. And I suspect that what we're hoping for is that you will all take this model, find a way to break it, tell us how it's not working, and then we'll fix it. Okay. So with that, I have in the top photograph, we have Pete McCauley, who's done most of the work, is on the right. And then 3 other mathematicians that have worked with me on this model. Lena Kalichev on the left is probably the most advanced mathematician in our team. He is really, really, really good at differential equations, much more complex than what we have used, but extremely helpful. And then below that is the core of my team in the experimental lab. You've seen earlier photographs of that. And then this work's been funded, the experimental work's been funded by more than 40 different agencies, but the mathematical modeling is not so much. That's just NASA, Air Force Office of Scientific Research, Regional Airline Association, and FedEx for their cargo operations have been funding this work. And with that, I think I'd love to take your questions. Thank you so much for your attention.
Hey.